Our previous episodes covered the transformer, but this paper, Attention is All You Need, really started it all. What central problem did it address?
Traditional models like recurrent neural networks struggled with processing sequences in parallel. They had to go word by word, making them slow and limited for very long sentences.
Before this paper, the best sequence models often combined recurrent networks with an attention mechanism to link encoders and decoders, improving focus.
We've touched on attention before as a way to focus on relevant parts of input, but this title, Attention is All You Need, suggests something more radical, right?
Precisely. The paper's radical proposal was to build a new architecture, the transformer, solely on attention mechanisms. It completely abandoned recurrence and convolutions.
Dispensing with recurrence and convolutions entirely? That sounds like throwing out the established playbook. Why take such a drastic step?
The main motivations were twofold: improving quality and enabling massive parallelization. Recurrent connections forced sequential processing, a bottleneck for modern hardware like GPUs.
So if you remove those sequential dependencies, you can process different parts of the input simultaneously, leading to much faster training?
Exactly. Imagine an assembly line where each step depends on the previous one. Recurrent networks are like that. Transformers redesigned the line so many steps can happen concurrently.
That immediately makes sense for speed, but how does it maintain this sequential understanding that RNNs got from their hidden states? Isn't word order important?
That's the brilliance of attention. It allows the model to look at all parts of the input at once, weighting their importance for each specific word. Positional encodings help preserve order.
So instead of remembering past steps, it explicitly calculates relationships across the entire sequence in one go? Right, so how do these positional encodings actually work? Are they just another input?
They're a clever addition. Before feeding words into the transformer, we create special vectors for each position in the sequence using sine and cosine functions of different frequencies. We then add these positional encoding vectors to the input embeddings. This way, the model gets both the meaning of the word and its position in the sentence.
The results were compelling. On machine translation tasks, the transformer models showed superior quality and achieved new state-of-the-art results.
An improvement of over 2 blue points on English to German is significant. That's not just faster, it's a clear improvement in translation quality.
Yes, and crucially, they achieved these results with a small fraction of the training costs compared to previous best models. Faster and better. That's a game changer.
This really established attention as a powerful primitive beyond just an add-on. It is the model's core engine.
We've seen why transformers matter. Now, let's peek inside this architecture and understand how its foundational self-attention mechanism works.
The paper, Attention is All You Need, is dense, but this illustration promises to oversimplify things a bit.
I'm ready for that.
At a high level, the transformer takes an input sequence, encodes it, then decodes it. The encoding component is a stack of encoders, and decoding is a stack of decoders.
So it still has an encoder-decoder structure, but each of those boxes built differently than an older model?
Each encoder has two main sublayers. First, a self-attention layer, followed by a feed-forward neural network. The decoder adds a third attention layer.
Self-attention sounds like it's looking within itself. How is that different from the attention we saw linking an encoder to a decoder?
With self-attention, as the model processes a word, it looks at other words in the input sentence to help encode that specific word.
So if the sentence is, the animal didn't cross the street because it was too tired, and the model is processing it, self-attention helps it connect it to animal?
Exactly. This is crucial for understanding context. While RNNs use a hidden state to carry information forward, self-attention explicitly bakes in relationships between all words.
The source says, self-attention is the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing. That's a good mental image.
To calculate self-attention, we first create 3 vectors for each word: a query, a key, and a value vector. These are projections of the word's embedding.
Query, key, value. This reminds me of database lookups. Is the analogy similar? Querying for a key to get a value?
That's a great intuition. It's similar in that a query seeks information using keys to identify relevant values. However, unlike a traditional database lookup where one query might return a single record, here your query simultaneously queries against all available keys, and instead of getting one value back, you get a weighted blend of all values. It's more like asking a room full of experts a question, and each expert, key, offers how relevant their knowledge, value, is, and you form your understanding by proportionally integrating all their responses.
So, a word's query vector will compare itself to all other words' key vectors to determine relevance.
Precisely. First, we compute the dot product of a word's query vector with all other words' key vectors. This gives us initial scores for relevance. Then, crucially, we divide these scores by the square root of the dimension of our key vectors. Let's say square root of dk. This scaling step prevents the dot products from becoming too large, which can push the softmax into regions with tiny gradients, making learning difficult. After scaling, we normalize these scores with softmax.
And these softmax scores all add up to 1. This gives us clear weights, essentially a probability distribution, on how much to attend to each word.
The final step is to multiply each value vector by its corresponding softmax score. Then, these weighted value vectors are summed up to produce the output for that position.
This weighted sum means that words with higher scores, more relevance, contribute more of their value content to the final representation of the current word.
That's it. The output vector for a word in the self-attention layer is essentially a blend of all other words' values weighted by their relevance to the current word's query.
This allows the model to process each word, getting its context from all other words simultaneously. No more waiting on previous calculation. So, one set of query key value vectors for each word and one attention calculation. Is that the whole story for attention in the transformer?
Not quite. The transformer uses multi-head attention. Instead of just one set of QKV projections, it performs multiple parallel attention calculations, each with its own learned QKV matrices. Think of it as having several different sub-attention mechanisms, each learning to focus on different aspects of the relationships between words.
So each head might look for different types of connections, like one for grammar, another for semantic similarity?
Exactly. This allows the model to jointly attend to information from different representation subspaces at different positions. After each head calculates its weighted sum of values, all these results are concatenated and then linearly transformed back into the desired output dimension.
Okay, we've deeply understood the self-attention in the encoder, where it helps understand the input sentence. But the decoder also has an attention layer. How does that one work, especially when it's generating new words?
That's where cross-attention comes in. The decoder's attention layer, specifically the encoder-decoder attention, doesn't just look at its own output so far. Instead, it creates its query matrix from the layer below it, which is part of the decoder's current state, and takes the key and value matrices from the output of the encoder stack.
So the decoder is asking questions about what it should generate, but it's looking back at the original source sentence encoded by the transformer's encoder to find the answers.
Precisely. It's a way for the decoder to focus on relevant parts of the input sentence as it generates each word of the output, ensuring coherence between the translated output and the original input.
We've built the transformer's core. Now let's see how it became the bedrock for a major leap in language understanding with BERT.
BERT, that's bidirectional encoder representations from transformers, right? The name itself tells us it's using what we just learned.
Indeed, BERT introduced a new language representation model that leveraged the transformer's encoder stack, but with a critical difference: true bidirectionality.
We talked about self-attention looking at all words. How does BERT take that bidirectionality further than a standard transformer encoder?
Unlike previous models that only considered context from left to right or right to left, BERT jointly conditioning on both left and right context in all layers.
So it's not just looking at the whole sentence for one word. It's doing it simultaneously for every word, considering both sides deeper in the network.
Exactly. This deep bidirectionality allowed BERT to learn a much richer, nuanced understanding of language, which is essential for complex tasks like question answering.
This pre-training phrase always comes up with BERT. What does pre-train deep bidirectional representations from unlabeled text mean in practice?
It means BERT learns general language patterns by training on massive amounts of raw text, predicting masked words and sentence relationships without needing human labels for each specific task.
So it builds a foundational understanding of language structure, grammar, and context before it even sees a specific application?
Precisely. This general knowledge makes it incredibly powerful. Once pre-trained, the BERT model can be fine-tuned with just one additional output layer for specific tasks.
That's a huge shift. Instead of building a specialized model from scratch for each NLP task, you can adopt a highly capable generalist with minimal effort.
It drastically simplified the NLP workflow. Suddenly, state-of-the-art performance became accessible for a wide range of tasks without substantial task-specific architecture modifications.
This is the reusable tool aspect of this idea. A well-trained transformer encoder can be a powerful building block for many language problems.
The empirical results were astounding. BERT achieved new state-of-the-art results on 11 natural language processing tasks.
Outperforming previous models by significant margins across a whole suite of benchmarks really solidified its impact. So transformers seem almost magical. Is there anything they struggle with or any inherent limitations in their design?
While revolutionary, they aren't without their challenges. One significant limitation is their computational cost. Self-attention requires comparing every word to every other word, meaning the calculation scales quadratically with the length of the input sequence. This makes processing extremely long texts very expensive and can be a bottleneck. There's a lot of research trying to make attention more efficient for longer contexts.